Okay, so far we have already discussed about some aspect of signals like Fourier series, Fourier transform, and then energy spectral density, power spectral density, what are the significance of them, given one example why autocorrelation function is important to evaluate energy or power spectral density. So this is something we have already covered. Now let's see, so far there were some touches where we could talk about communication, but we have not gone inside the communication aspect. So today what we will try to do, actually try to see how this understanding of signal can make us to communicate, okay, or can aid us to communicate. So this is something which we will be targeting today. So if we start seeing communication as we have discussed earlier, so there are two aspects of communication. So one is of course the signal, which is the source, that's the thing that has to be communicated, and the other part is the system, which somehow there is a transmitter receiver in between a channel. So either the transmitter or receiver processes the signal. So this system, receiver or transmitter, are actually a system which processes the signal towards a desired output, so that the signal can be transmitted faithfully at the receiver side and all the information can be faithfully transmitted. So this is the purpose of the system design, right. So system design has some purpose because it operates on a signal. So any system that we are targeting must serve those purpose. So for a communication system, the most important part, as we have so far explored, is probably the modulation and demodulation. So this is the first thing we will be exploring, that how to devise a system that does modulation and demodulation at transmitter and receiver respectively. Okay. So if we just start seeing communication, there are in a way two types of communication. One is called baseband communication, and the second is carrier communication. Okay. So what do we mean by these two? So baseband communication means we actually transmit it as a low pass signal. Okay. So whenever we are transmitting, if in the frequency domain we try to see, it will occupy some low pass band. Okay. So that is generally called baseband communication. So why it is called baseband communication? Generally the signals that we generate, the raw form signal, let us say we generate a voice signal through a transducer. So basically we talk, the transducer converts it into a electrical signal. If we just try to see how that electrical signal looks like, we will see for voice signal, it occupies a band starting from 300 Hz towards 3.4 kilohertz. So it occupies some band like this, and of course because it is a spectrum and it is represented by Fourier transform form, so it should be having equivalent negative part. So minus 300 to minus 3.4. So this is typical voice signal that looks like. If you have the two most popular signals probably were one was voice signal and the other one was which was popularized by radio transmission. Okay. So and the other one was probably the video signal. Okay. So if I just try to see the video signal, that has a higher band, that means again there should be a video transducer which converts the video signal into equivalent electrical signal. So what it does actually, if you have a screen, so every second there are few frames, so frame represent the entire screen, and then you have pixels on the screen. All those pixels will have their own grayscale value if it is black and white. If it is colored, then there will be three composite colors, and each color will have their own value, grayscale value again. So those signals has to be, means if I just put them on time, so for each frame we just one after another pixels value we put, we get a signal, and that particular signal, if I just represent it in electrical domain the way I have told. So basically if you have a screen, you scan them pixel by pixel from this direction left to right, again you do for the next line and so on, you do all lines. Every pixel value you put a voltage, next pixel value you put another voltage, and you put it on time. So this is overall frame. If you do, that will be one frame followed by another frame and another frame, so on. So you get a signal, equivalent electrical signal. And if you just again do a Fourier transform of that and you represent it in frequency domain, you will see that it occupies up to 4.5 megahertz. Okay, so that's quite big. Of course, the video signal has a higher bandwidth, or it occupies a higher bandwidth. So this is the raw video signal. As you can see, these are all low pass equivalent signal. Okay, so it's centered around 0, and through a low pass filter you can always extract that signal. Okay, so low pass filter bandwidth has to be accordingly adjusted. So these are the signals which are, means if raw signal I wish to transmit, that will be termed as baseband signal. Okay, so if I wish to transmit that, it should be a baseband signal. That's about baseband signal. Even telephony, which is probably we have already talked about telephony. So what happens there? Also we transmit voice, but the voice is encoded. So basically, if I in the last class we were demonstrating that the voice I'll be sampling, each sample will be represented by binary bits, and if we just transmit that binary bits, we have already seen that a random sequence of binary bits, if I just see the spectrum through autocorrelation, we have drawn the spectrum. Autocorrelation was something like this, and the corresponding spectrum was sync square, right? So it was like this. Again, if you just see, it's a low pass equivalent signal. So these are all baseband signal. If I wish to transmit them raw, this will be baseband signal. So, and the corresponding communication will be termed as baseband communication. So I don't do any modulation over here. That means I don't put it in any higher frequency. Okay. So as long as I am not doing that, that particular communication is termed as baseband communication. If instead, we have already talked about frequency division multiplexing, that means in frequency domain, I wish to put those signals which are band limited in different frequency location. Okay, so that I can multiplex multiple signal and simultaneously transmit them. They are in time domain, they will be overlapping. Okay, but in frequency domain they will be non-overlapping, and I can always employ a band pass filter to extract my own desired signal. So basically, a meaningful transmission can be, or simultaneously multiple meaningful transmission can go through the channel. Okay, it can utilize the same channel, and I can transmit multiple signals. So that is the basis or the basic requirements for doing a modulation. Okay. We have also discussed that there is another reason why we should do modulation, that was typically for radio transmission. So if we wish to broadcast the signal, that has to be received by an antenna, and the antenna size has to be comparable to the wavelength of a signal. So this is something we have already discussed, that if I wish to do that, the frequency has to be higher. So I should, instead of, if I wish to transmit baseband signal, antenna size will be very big. Instead of doing that, same signal I can actually modulate. It will serve two purposes. First of all, because it goes to higher frequency, my actual antenna which catches this signal will be much smaller, and then after that I can employ a low pass filter to extract that signal and then do a demodulation to get that signal again back to baseband. Remember, the signal is by itself is defined in baseband. So if I wish to again either listen to that voice or watch that television, I need to convert that to the baseband. So my demodulation actually means, if I do a modulation, then demodulation actually means again from that passband I have to bring that signal to the baseband. So this is all that we mean by demodulation. So definitely now you can see that there is a purpose, two purpose probably. One is for multiplexing, another one is for reducing the antenna size. We need to do modulation, and that's when the first hurdle of communication comes into picture, or first design of system comes into picture, that I have to now devise a system which modulates the signal, that means does the frequency shifting, and I have to design a signal which demodulates, or system which demodulates the signal. That means already modulated signal I can catch through antenna. After doing low band pass filtering, I need to demodulate it to bring it back to baseband, so that I can put it to the transducer and again either listen or watch whatever I wish to do. Okay. So let us try to see what this modulation means and why we are saying that to be a carrier modulation, okay, or carrier communication. So let us say, whenever we are talking about carrier, I have a signal. I am just representing a sinusoidal signal. So sinusoidal or cosinusoidal, it must have a cos, and it has actually 3 parameters. One is the amplitude of this cosinusoidal, which I can write as A. The other one is the frequency of this cosinusoidal, which I can write as omega c or 2 pi fc, whichever way I wish to write, into t, plus there should be a phase, right? Let us call that phi. So this is a cosinusoidal at frequency omega c, and generally what we say, because this is at some frequency, we call that a carrier. Why it is carrier? That will be clear, because it does not by itself carry any message or any information. It somehow modulates the message that it carries. So that is why it is a carrier. It is almost like a envelope that carries your letter. Okay, so it just helps you to carry the letter. It has no importance, just it has to carry the thing that you are trying to transmit, just delivers it to the destination, and after that it has no usage. So you will be again demodulating, so you will be getting rid of this carrier. Okay. So right now we can see there are 3 terms in the carrier. So while modulating, I can use one of these 3 to carry my signal. Okay. So suppose I have a message. Okay. What I can do, I can either make this amplitude time varying, which is proportional to my message signal. Okay. So that way also I can carry my message signal on top of this one, or I can vary the frequency with respect to time, which is proportional to my message signal. Again, over a frequency I am carrying the signal, or I can vary the phase proportional to my message signal, and accordingly there will be different kinds of modulation. So if I carry it in my amplitude, that is called amplitude modulation, AM. If I carry it through my frequency, so that is called frequency modulation, or popularly termed as FM, and if I carry it through my phase, then that is called phase modulation, or PM. So accordingly there will be 3 kinds of different kinds of modulation, which has their own advantage, disadvantage. They will have their own types of system designing. We will see those things. So we will try to explore these things: amplitude modulation, frequency modulation, and phase modulation. So these are the 3 predominant analog form of modulation that exist. Of course it is going over a cosinusoidal carrier. Okay, so the carrier is there and I wish to do some modulation. So initially for the beginning of our course, probably we will be more concerned about amplitude modulation. Later on we will explore the other things, which are these 2 are again termed as angle modulation, because overall this can be termed as a phase of a cosinusoidal. Okay, it has a frequency part, it has a phase part. So overall I can talk about, with the t in it, we can talk about that is the overall time varying phase or the angle. Okay. So that is why it is called angle modulation, or I should not write AM, then it will be confused with amplitude modulation. So it is actually angle modulation. Okay. So initially we will be concerned about the amplitude modulation. So let us try to see the most basic form of amplitude modulation. So we have told that in amplitude modulation, my message, let us say I have a message signal which looks like this. Okay. So some message signal, this looks like this, it is empty. Of course it might have random variation, as we have already termed about it, that if it is a voice signal for the receiver, it must be a random signal. So anyway, it is some kind of signal, okay, which is time varying, and the time variation might be random. And on top of that, we also have another requirements that this must be band limited. That means if I take the Fourier transform, how we will be taking Fourier transform? Again, we will be probably knowing the statistical property of this, and we will do our time autocorrelation function, and we will do a Fourier transform. So, we will get some Fourier transform. Let us say this is the Fourier transform of this one. Our requirement is this Fourier transform should be essentially band limited. Okay. So, that means the frequency terms that are existent for this signal are essentially within certain band, or otherwise we can say if it is not band limited, the out of the band or whichever band we are targeting, beyond this there might be some frequency component, but those are insignificant. Okay. So, we do not have to be bothered about that, whether that is transmitted or not, that will not distort the signal beyond something beyond our perception. Okay. So, we will say that this is band limited. So, this goes from minus B to plus B. Okay. Right. So, I have a signal now, which is a random signal probably, which has a equivalent Fourier transform representation, or I should say a power spectral density I have. Okay. So, these two things are there, or I can always say it has a means MF, correspondingly it will have mod MF square, which is either energy spectral density or power spectral density depending on how you define it. Okay. So, we are just right now thinking about that we have a signal and we have corresponding amplitude spectrum. That is the simplest way to represent it. Rest of the things can be done later on. Okay. So, these two things are known, suppose, for a signal. Now, we have to design a system which does modulation. So, what we need to do, the first way of doing modulation is frequency, using frequency shifting property of Fourier transform. So, if I have MT, we have already told that it should be carried by the carrier. So, MT must come over here. So, my modulation must look like MT cos omega ct plus some phi, constant phi, which must not be time varying, because we are just putting the message in the amplitude, not in frequency or phase, that should be remaining constant. So, even for simplicity we can take that as 0, even if you take a constant value that will not disturb you. Okay. So, we can say this is my modulated signal. So, here the terminology will be, this is my carrier, this is my modulating signal or the message signal, and this is the modulated signal. Okay. As you can now see, we are familiar with this already. So, if ST becomes MT cos omega ct, immediately if I do Fourier transform of this, so SF should be, we have already derived this, that is the famous frequency shifting property. So, that becomes MF plus, suppose this omega c is 2 pi Fc, and should be F plus Fc plus MF minus Fc, right. We are saying this is our amplitude modulation. So, how the spectrum will look like? So, if I was having MF like this, whenever I modulate, that goes around Fc and minus Fc, and the corresponding strength becomes half. So, if this is like this, this will be half of that, right, the amplitude will be half of that, but the shape will remain the same. So, that is the MF minus Fc, and this is the MF plus Fc, and you can see after modulation, because it is a real signal, so it is a event symmetric representation. Okay. So, the conditions are that this F minus E, whenever I modulate, there are two things which are happening. What was the bandwidth of this signal? The bandwidth was, it is up to B, right. So, the overall bandwidth is 0 to B and 0 to minus B, negative half I can ignore to define bandwidth. So, it is actually bandwidth is B. So, the baseband signal has bandwidth B. Whenever I do modulation, what happens, because the shape remains the same, this should be Fc minus B and this should be Fc plus B. So, overall bandwidth will be doubled, that is called 2B. Okay. And what happens, if you see, this signal was even symmetric. So this particular half and this particular half, this half does not carry any extra information. As long as I know the pattern of this half, that will be repeated in the just in a, as a mirror image in the other half also. Okay. So basically the information is contained in one half, or within, if I say just baseband, then within that B bandwidth. What is happening after modulation? My bandwidth is getting increased. Now the overall bandwidth, if you see, it is defined from Fc minus Fb to Fc plus Fb. Just if I see the positive half, negative half we do not have to see for bandwidth calculation. So that becomes 2b, and what is happening? This is still even symmetric. See, this is symmetric, and plus around this, because the shape remains the same, around this point Fc, it is still even symmetric, or it is symmetric. So still the information is carried by this particular band only, which we term as upper sideband, and this particular thing we call as lower sideband. And upper sideband or lower sideband are just mirror image to each other. So they do not carry extra information. Whatever upper sideband carries, same information about that signal is being carried by lower sideband. But unfortunately, whenever I do modulation, I will be requiring this entire 2B band to transmit my signal. So what is happening? Eventually my signal bandwidth is B, but after doing modulation, I am occupying at least 2B band, and that is being occupied by me, my own signal. So in a way there is a bandwidth wise, if you start asking, there is a wastage, or I should say double wastage, because for every B bandwidth signal I am occupying 2B bandwidth. Later on we will see if we can have some bandwidth efficient modulation technique, but right now we should be content with that. This is the simplest form of modulation. I just do this, I get this particular thing. I know that bandwidth wise it is not the most efficient one. And of course, you will be requiring this because bandwidth is a commodity. You can see that if you have some certain band to operate, you will be putting your signals one after another, and they should be non-overlapping if they are band limited. So basically, how many signal you can put within that band will be restricted by what's the band it is occupying. So therefore, if you can reduce the band, of course it will be occupying more number of signals, that means more number of simultaneous transmission you can do. So here what will be happening, if you just do this modulation, as many for same band, suppose where you can operate, if you can operate with n number of, means you can transmit n number of simultaneous communication, what will happen? If I could have reduced this to half, I could have transmitted twice that number. That is a big number. Suppose I can transmit 6 radio channel over a band, now I can say I can transmit 12 radio channel within that same band. So cost wise that will be much more effective. We will be definitely targeting that, but right now we should be content with this modulation. So this particular modulation is called double sideband with suppressed carrier. Okay, we will talk about why it is suppressed carrier. Right now it is double sideband, that is clearly understandable because we are transmitting both the sideband, upper as well as lower sideband. When we are, see, after doing modulation we will be putting it in the antenna. Now it is actually serving me two purposes. One is it has been translated to a higher frequency, so the antenna size will be smaller, and it is occupying a particular band, so I can actually multiplex. Okay, if I was trying to transmit raw baseband signal, two voice signal will be occupying same baseband, and we won't be able to multiplex them. So two purposes are being served. Another thing that has to be seen is what should be my FC. Very carefully see, if I have chosen my FC over here, okay. So my signal, whenever I modulate, it will be left shifted and right shifted. So what will happen? This two things, after left shifting and right shifting, they will overlap with each other. And in the frequency domain, you cannot actually separate them. Now you cannot employ any filtering technique to separate them out. Okay. So what will happen? Your signal will have some distortion, because this gets overlapped, so it will look like something like this, which is a completely distorted version. If I just, so it still remains a low pass signal which has a frequency, suppose I am centered at Fc. So it goes up to fc plus b, and it is of course minus fc minus b, right. So now I cannot employ after doing this modulation, I cannot employ any kind of band pass filtering. So I will have to employ a low pass filtering of bandwidth fc plus b, okay, and that will distort the signal. If I now put it in the of course it is already baseband, so if I just try to see the time domain signal, it will be distorted because the frequency components has been distorted, so signal will be distorted. So therefore if I don't wish to have distortion, what I need to do is at least I should ensure that whenever I put them, they are separated. So that means my fc, this fc must be bigger than the b, and generally it should be much bigger than the b. So that is some criteria which has to be satisfied. Whatever modulation you do, wherever you wish to put, but you have to always ensure that whatever frequency you are choosing for your carrier, that must be greater than the bandwidth of the signal. And that is why it is very essential that you know the Fourier or energy spectral density of your signal you are modulating. Voice, whichever way you are modulating, because it has a much lower bandwidth, if you employ the same thing for video, probably it will not work, because video is occupying a much bigger baseband frequency. So you have to accordingly see where I can put, which particular frequency I can choose and put my video signal. That is very essential. Whenever you are doing modulation, that is one part which is essential, and also you have to see what frequency you are choosing, because accordingly your antenna size will be decided. So both the things will actually determine what frequency you should choose. Okay. Now let us see what happens to this DSB-SC. So basically what has happened, I have a signal MT. For modulating, what I have to do, I need to multiply it with cos omega ct. So basically from signal I am now trying to devise a system, okay. So what I need is a multiplier circuit. Somehow I have to realize this multiplication. A circuit which where I will be giving two input, one is my message signal itself or modulating signal MT, and I will be giving a carrier signal, and somehow my system should multiply this. We will see how this multiplication can be done, and then the output will be MT cos omega ct. For my purpose, this is my modulation. So if I can realize a multiplier circuit, that makes my modulator system ready, and then I just put it in the antenna and it will be transmitting this particular signal, because this characterizes what I wish to achieve in modulation. Okay. In time domain, what will be happening? So suppose I had a signal which I have shown earlier. If I wish to modulate it, so basically what will be happening? I am modulating with a carrier frequency which is cos omega ct. As you can see, the time varying of amplitude which is much slower than this time variation, because it is at very high frequency. Okay, so that will be happening. Now if I just multiply this, the amplitude of this one, this carrier frequency must carry this signal. So this must be reflected in the amplitude. So what I will see is something like this. This should make my envelope of the carrier. So if I just envelope means it should be from both sides. So that draws the envelope. Within that the carrier will be oscillating, or it should be, if this is 0, sorry, if this is 0, let me draw it again. There will be something happening over here. We will discuss that in the next class, but this is what will be in the time domain, okay, where in the envelope the message will be carried over.